So yeah, hello everyone. So my name is Wan Rabion. In this video, I want to walk you through a paper that I work called Adaptive Conformal Prediction for Reliable and Explainable Medical Image Classification. So this paper was actually joint work with my professor. In this video, I want to go deep into the paper. Um, Maybe I'll show you some numbers, formulas, and try to draw everything on the slides so we can see actually how the model or the method works step by step, something like that. So yeah, let's get started. So the first one is the motivation of this paper. The core problem, as we know, like in normal classifier like ResNet, it takes an image and gives you softmax probabilities, something like a 95% spleen. But the true answer was actually a bladder, like this image. So the model was very confident and very wrong at exact time. And why does this happen? It's because of how we train these models actually. Because like we use cross entropy loss, and cross entropy pushes the model to put almost all the probability mass on one class, even when the image is generally ambiguous. Maybe let me write this softmax. So maybe something like this. So the softmax just transfer scores or logits into probabilities that sum to one, but cross entropy loss during training is actually something like this. So to make this loss go to zero, the model is rewarded for pushing p through class as close to one as possible, even when like they have a fuzzy or ambiguous image. There's no mechanism telling the model like, hey, it's okay to be unsure here, like something like that. So yeah, that's the root of the overconfidence in this normal model or classifier model. And the sneaky part is the accuracy. Um, the metric that everyone use is an average over the whole data set. So if we have maybe like 90% accurate, that actually tells you nothing about whether the specific patient or image is was classified accurately. So some individual prediction can be like systematically wrong, and average accuracy will never reveal that. Um, and so how do we fix this? The answer in this paper is conformal prediction. So to sum up, instead of asking the model for one label, we ask it for a set of labels. Set of labels, uh, which we call it a prediction set, and this set is comes with mathematical guarantee, something like this. So the probability that the true label y is in set or prediction set is at least 1 minus alpha. And in our paper, the alpha was set to 0.1, So actually that is a 90% guarantee, and not like 90% accuracy. So 90% guarantee that the true answer is somewhere in the set that we return. And the beautiful part that this is distribution free, so we don't assume anything about the model or the data. It just works using white clever trick, like split conformal prediction. So let me show actually how with real numbers, because I think this is the heart of our whole method. So maybe wait. Maybe we have let's simplify to 5 organ classes instead of 11. So we have liver, spleen, kidney left, and kidney right, and pancreas. Let's say uh, so for let's say for one calibration image, the true label is kidney left, and the model gives us something like liver, uh, yeah, sorry, then kidney, which is the true label, and then kidney right, and pancreas. And when we sort this from biggest to smallest, we have rank 1 is kidney left, and etc. Now, the then we have the conformity score. Basically, like how surprising is the true label. We take the cumulative sum of probabilities up to and including the rank of true label. So since kidney left is rank 1, we only need to sum up to rank 1. Let's say like, yeah, the score is like this. Let's score 0.35. And if kidney left had been ranked 3 instead, so yeah, the score would have been like mm, maybe in here. Yeah, something like this. Much bigger score, meaning that the model needed to go deep into the ranking to find the truth. So the bigger score mean that the model was more surprised. Model more surprised. And yeah, we do this for every image in our calibration set. Get 1 score per image, and now here's the calibration trick. Um, Say we have n calibration image, small on purpose to show just how important it is, and their scores sorted are maybe like yeah, something like this. and 0.4 maybe. We want an alpha equal to 0.1. So we want like the 90th percentile, the formula and the formula of conformal prediction uses is something like this. Um, let me just yeah, gives give hat something like this. 1 minus alpha, the small score. So when we plug it the number, we have yeah, maybe let's just so then 9 plus 1, then 0 times 0.9, we still have 9. So the 90th small score out of 9, which is the maximum, we have this 0.40. And notice something that interesting with only 9 calibration points, satisfying a 90% guarantee sometimes forces you to take the single worst or the biggest score you've seen. And this plus one in the formula it's not a typo. It's what makes the finished sample guarantee mathematically correct. So it's a bit conservative on purpose. And with more collaboration data, maybe like 12,000 of images, like we have in this paper, the quintile becomes much more stable and less extreme. Now, at this time, for a new image, we don't know the true label, so we do the reverse. We add classes into our prediction set, starting from rank 1 until the cumulative probability crosses into 0.40. And our organ, example, like rank 1 alone, kidney left, 0.35 is not enough because it is like less than 0.40. So then we add the rank 2 spleen, which we have 0.30. And then like the cumulative one, it's 0.65, which is greater than equal to 0.40. And the final result set is we can have this kidney left and spleen. Exactly like that, the example. Then let me go to next. Then we have this. The marginal coverage can hide local values. So this is actually a trap. The 90% guarantee that I just showed you earlier, it's called marginal coverage. So it's an average over the whole test set, and averages can hide really bad local behavior, I think. Let me show you, I think, with the real numbers from the paper. So let's say we have two groups, maybe like easy group, which they have around 70,000 images, and hard group only 10 images, and the coverage is 93%, and this one 60%. Now when we compute the overall weighted average, we have um, uh, times then we have something like or 92%. When we look at this, the overall number still looks great, like 92%, but actually those 10 hard cases, the ones where the model is generally confused, are only correct 90% of the time. So the marginal warranty is satisfied, but it's quietly failing exactly where it matters the most. And this is central motivation of the wallpaper. We need to check coverage not just overall, but within each difficulty group, what we call it a stratum. And the natural way to define difficulty here is how big is the prediction set. Size 1 means confident. Size 2, 3 and more means uncertain. And yeah, something like that. And let me go to next. So, and quickly, where does this set compare to other work? First one, we have class conditional or modern conformal prediction that calibrates separately per class, but that is a different sizing because it's not per prediction set size like we have. And then we have RPS or regularized adaptive prediction sets from Angelo Bolus and his friends. And it has already have a knob called lambda that can control set size, and they even mention that you could tune it for stratified coverage. And our contribution is we actually do that tuning systematically with a clear objective function, and we test it specifically on medical imaging with two different modalities or data and connect it to Grad-CAM explainability. So yeah, let's get into RPS, I think. So this is the most important formula thing in the wallpaper. So let's put it, I think. So the base score, wait, wait, so yeah, the base score first set. So so this is actually what I computed before, a cumulative softmax that match up to the true label strength. But in that uh, thing, it's actually have they are non-problem also. With just using this base score on hard images, this cumulative sum can drag in a lot of low probability classes just to cross this threshold, making the prediction sets huge and useless. So RPS adds a penalty term, something like lambda something like this. We have two new symbols here, which is key rec. Basically, the first key ranks are free, no penalty, just threshold, something like that. And then we have lambda. That is how harshly we punish when we're going deeper than key rec. And maybe for the example, let's reuse our 5 organ softmax numbers before. Rank 1, kidney left 0.35, rank 2, spleen 0.30, rank 3, kidney right 0. Then liver, then pancreas, let's set K-rec 2 and lambda 0.02 and compute the RPS score for two different true labels. For case 1, case A, true label is kidney right. True label is K-rec, kidney right. That the rank is 3 here. So when we compute it, then the penalty lambda max max of so the RPS something like 0.92, and for the case B, when we have true label is pancreas, where we have the rank is 5. The space is around 1. So when we have the penalty is reps, it's just gonna be see like what happened, so both scores got pushed up, but pancreas, which needed to go really deep in the ranking, got pushed up more, like 0.06 versus 0.02. This is the penalty that actively discouraging huge prediction sets. So the bigger lambda is, the more aggressively RPS shrinks the sets, and that's the actually danger, because if lambda is tuned too aggressively, it can shrink sets so much that hard. Ambiguous images never get the extra credits they needed. And that's exactly the failure we saw in segment 3. And one more detail, for the minimax optimization later, we don't look at every possible set size individually. We group set sizes into strata. So, for example, G1 is uh, have the variation just like here, like this. Then G2, 2, 3, G3 maybe 4, 5, 6, and etc. to G6 maybe 1, 0, 1, 2 until K. And yeah, for all like 11 class or 9 class problems, the upper groups G4 to G6 stay empty, but this design keeps the method general for problems that with way more classes. And then now, yeah, the actual contribution of this paper is actually like how do we choose lambda so that we don't repeat the mistake from segment 3, like standard RPS usually picks lambda to minimize average set size. So instead to pick lambda using yeah, so instead we pick lambda using minimax rule over strata. So the formula is like this. Um, in this minimax formula, we have coverage. Actually, the fraction of correctly covered true labels measured only within stratum M using a particular lambda, and then coverage minus 1 minus alpha is how far off that stratum is from our 90% target. Could be too high or too low. We take the absolute value and then max. Actually look across all strata and take the worst or the biggest gap. This is the minimax part. We care about the worst case stratum, not the average one. And then the up minus. Try many different lambda values and pick whichever one makes the worst case gap is as small as possible. Okay, so for minimax example, let's make this concrete with simplified maybe two strata. Maybe we have something like this. G1, which is singleton, have then G2 multi-label, and then the target 1 minus alpha is 0. So first we try lambda 0.001, which is fairly aggressive. So first coverage G1 is 90% and the gap is then coverage of G2 90%. The gap is then we try maybe lambda with 0, lambda 0, so it has no penalty at all. G1, the gap coverage for G2, 0, the gap. Okay, let's see. We can compare 0.30 with which is with lambda 0.01 versus 0.03 with actually uses lambda 0, which by a mile, like the worst script gap is 10 times smaller. And this is not just a random. This is literally the real what I really found. So the actual result um, on both data sets, like the criterion selects lambda 0 and then K-rec is 1. So in real experiments, the minimax search scanning over a grid of lambda values from 0 to 0.002 found that lambda 0 was literally the best choice. So in other words, don't add any extra penalty for going deep into the ranking. Just use the raw cumulative softmax score. Maybe that sounds almost too simple, but it makes sense because any penalty at all was shrinking the hard multi-level versions too much, I think. So hurting exactly the group we're trying to protect. Let's say the grid that used in paper. So maybe you know the actual search page user like grid. So every one of these egg values gets tested across all 6 data, and we give whichever one minimizes the gross wall scrap. That's the wall algorithm, I think. Let's get to the next. Then quick setup recap before the results. So ResNet 80 pre-trained on ImageNet, dropout 0.3, label smoothing 0.1, train with Adam and Cousin schedule. Data comes from MNIST, organ MNIST, which is uh, uh, 58,000 of abdominal CT images across 11 organs, and PET MNIST, which is 100,000 colon pathology images across 9 tissue types, but originally tiny, like 20 by 20 by 20, 28 images upsample to 224 for the network. So we compare 5 methods like naive thresholding, LSE, RAPS that tune for size, and then RAPS with temperature scaling, and our adaptive RAPS. And then the results on organ MNIST. Let's read the results table together. So focusing on numbers that matters most. So look at um, the middle of column first, average set size. RPS size and RPS temperature are both basically one, meaning that almost every prediction is a single label, size 1. Sounds efficient, but when we look at the last column, like last stratum coverage, it collapsed around to 60% and even 40%. That is the exact failure from the segmenting, but with the real data. And those methods produce only 10 multi-label sets total out of around 70,000 test images. And even those 10, I think, are not reliable also. But when we compare to our adaptive method, average set size goes up just slightly around from 1 to 1.09, about 90% increase in effort, but worst rating coverage jumps all the way up to 94%. That's the safety efficiency trade that we are making. We pay a small of efficiency cost to get a big safety win. Then maybe maybe to visually, maybe like to let's make something like this to so you have a better understanding of this result. So G1 size 1 size 1 have 90% coverage, then G2 size 2 3 94 coverage with data run, then G3 97% coverage. So all three um, all of three clear the 90% target. That's the whole point of the method. So compared to RPS size, right next to it will the maybe be better to see it in this line. So where compared to RPS size, right next to it, the orange bar, multi-level cases offer 60% with only 10 samples. That is the visualization of this table. And then the second result. So does this generalize or is it a lucky result specific on CT scans? We rerun everything on PAT-MNIST or colon pathology images, totally different modality from before. So it's actually same story. Standard RPS again related to Mystic, average size around 1, and it is worse stratum drops to 75%, or method costs a bit more, but pulls worse stratum coverage up to 88%, same failure, same fix on completely different type of image. And I think that's a good sign of the method that is not just overfitted to one dataset quick. Then next section, I think this is the fun part. Can we actually see why the model expand its prediction set? There we use Grad-CAM, which produces a heat map showing which pixels the model look at most to make its decision. We have kidney left heat map image Notice that the hot or the red one region doesn't just sit on the kidney, it bleeds into the spleen and even the other kidney that matches the perfusion we saw in the per class table. So kidney left had the lowest position around 71%, precisely because of this bilateral symmetry, left and kidney right. Um, because it look almost identical and the spleen sits right next to the left kidney. Um, but look spread out is actually subjective. We need a number. So the number is called spatial entropy of the heat map. So is something like this. Uh, Something like this. So where pi is the normalized heat map value at pixel I. So think of something like this. So how much attention did pixel I get as a fraction of total attention? So when we compute this by hand on a tiny, maybe made up 3 by 3 heat map, just 9 cells. So you can see like how it behaves. So something like so it's uniform. So 9 times and log, then we get from 3.17 bits. This is the maximum possible entropy for online cells. So total uncertainty about where the important pixel is maybe uh, maybe case 2, yeah, maybe case 2 is focus attention. So maybe central cell P. So other Excel serves the rest equally. So each one. So each focus from step 1 you can get a log of around then term 1 around 0.13. Then for step 2 let me write here around 474. So term from each one is around 0.178 and term 2 1.42. So each focus is 1 bits, 1.78 bits. So when we compare, the uniform tension gives 3.17 bits, but focus attention gives 1.78 bits. But when we summarize, lower entropy, more concentrated and more certain looking attention, and this is exactly the direction the paper's real result goes. So from the table 5, mean entropy, singleton predictions, then mean entropy for multi-label, 5.60. So real images have way more pixels than our 3x3 toy example, so the actual entropy numbers are bigger, around 15 instead of 1 to 3. So but the traction matches our example, like multi-label, the harder, more ambiguous, so predictions have likely lower entropy than singletons. That seems backwards at first, but when you think about it, so confused means scattered attention. But what's actually happening is when the model is torn between two specific organs, its attention locks onto the specific quadri region between them. So a small, focused, ambiguous one, rather than spreading out randomly. So it's focused kind of confusion, not diffuse one. So then the correlation numbers, we have Spearman, then point visual, around minus 0.44. The Spearman correlation just checks that as prediction set size goes up, does entropy tend to go down or up? And negative p around negative 0.30 means that yes, there is a real consistency tendency for bigger sets to have a lower or more focus entropy. Not a huge effect, but a very statistically real, since the p-value is astronomically small with 1000 samples. And point visual is the same idea but simple, just splitting samples into two groups, singleton versus multi-label, and checking if the entropy distribution differ. And again, negative and highly significant, but so both tests are pointing the same direction. Set expansion is not randomized, and it's tied to genuine and localized visual ambiguity in the image. So next part, the limitations. So let me be honest about the limits. So the stratified coverage currently actually is not distribution free like the marginal one. It's more empirical heuristic, so tuned on the calibration data, and there is a theoretical result showing exactly conditional coverage is um, I think probably impossible without extra assumption. So what we build is a practical, a more tractable proxy, not perfect guarantee, and also math images are also tiny, around 28 by 28 originally. So some of the ambiguity may be related to the data set itself. So for resolution clinical validation, I think is future work. So and extending this minimax idea to maybe class conditional and essential coverage. Then the conclusion, um, the whole everything like this video and paper in one picture. So size tune RPS can hit its overall coverage target while quietly failing on the hardest, most uncertain cases, dropping to 40 to 60 coverage, exactly where the maybe patterns that needs reliability the most. And by choosing the lambda with a worst case stratified minimax rule, instead of plain size objective, we successfully bring that worst case coverage back above 90% of, and for a small cost about 90 to 12% bigger precision sets on average. Mm, this is not a one dataset fluke because we try on the other dataset and it just works. And also the visual explanation from the Grad-CAM picks up that the extra characters, the modelettes are generally tied to ambiguous anatomy, not random noise. Yeah, something. So I think that is the paper. So yeah, I think something like that. Maybe my explanation or my writing or something like that. Drawing is not uh uh yeah. I think that's all for me. Thank you very much.